In our previous video, we looked at the structure of our alkanes, which is one of our simple hydrocarbon classes, where we have carbons, which of course each form their 4 chemical bonds due to their 4 valence electrons. And of course with our alkanes, we only have single bonds between our carbons, and then we also have single bonds between our carbons and our hydrogens. Now, since each of our carbons here can form 4 bonds, we can create potentially very large structures with our alkane molecules. So for each of our carbons, we can use these bonds to add on additional carbons. So we can add on another carbon over here. I can add on another carbon. And I can keep this going as far as I want to. I can attach more carbons at the end. I could also replace one of these hydrogens here in the middle and create what I call a branch, where I add another carbon down here. For many of our common natural compounds, we'll have dozens or even hundreds of carbons involved in our full molecule. Even when we go to draw something with just these 5 carbons, we can see that it takes some time to draw our full structural formula for these molecules. So as organic chemists, we like to take shortcuts. And we have ways of representing our organic molecules more easily without drawing out every single carbon and every single carbon-hydrogen bond. So today we're going to look at some of the different ways that we can quickly represent organic molecules without taking the time to draw out every single carbon and every single hydrogen bond with those carbons, since we're going to have, of course, a lot of hydrogens with a large alkane or hydrocarbon molecule. So the first shortcut that we can use is our molecular formula. So as you should know from general chemistry, the molecular formula tells us how many of each atom we have in a particular molecule. So to get our molecular formula, we just have to count up all of our atoms. So we see here we have 5 carbons. We put that in here. You go C5 with that little subscript 5 indicating our 5 carbons. And then we put in our number of hydrogens. And we have 12 hydrogens here as well. Since actually each of our carbons will always have 4 bonds, this number is going to be, is actually predictable based on the number of carbons that we have. So for any alkane, if we have n number of carbons, we will have 2n plus 2 hydrogens. Right? So each carbon will have at least 2 hydrogens bonded to it, and then we'll have 2 extra hydrogens on either end. Right? Because each carbon will have at least 2 bonds to carbons on either side, except for the carbons at the ends. So this is kind of our general formula for any alkane, just based on how many hydrogens we need to give each alkane those 4 bonds. So we might think that this molecular formula here is a very simple way of representing our structural formula. However, we have a problem here, right? So if we take this C5H12, that's just telling me that I have 5 carbons, right? So I could write out my 5 carbons, and of course I have my 12 hydrogens, so I could add on all of my 12 hydrogens. And what we'll see, of course, is that this molecule looks different from the first molecule that I drew. Right? So we have all of our carbons here connected in a straight line. Over here I had my carbons in a straight line, and then this carbon coming off as a branch. So while these 2 molecules both have the same molecular formula, right, they have the same number of carbons and the same number of hydrogens, they have different structures, and these are in fact different molecules. We refer to these as constitutional or structural isomers. So these are two molecules that have the same molecular formula, but different structures in terms of how those atoms are bonded together, right? So they have different connectivity, we would say, where this carbon is connected to that carbon in the middle instead of being connected at the end like it is over here. So, same formula, different connectivity. So we need a better way to represent our molecule where we can actually show the structure along with, of course, indicating what atoms we have here. So as we saw, our molecular formula doesn't give us enough information to be able to distinguish between one molecule and its constitutional or structural isomer. So we're going to need something that will give us a little bit more information about our structure compared to just that molecular formula. There's a couple different ways that we commonly do this. The first thing that we'll look at is a condensed formula. So this is going to be similar to our molecular formula in some ways, but it's going to include extra details that will tell us how things are connected. So what our condensed formula does is it takes our molecule and it's just going to kind of condense our hydrogens down so that we don't have to add in all these extra hydrogens. So what we're going to do is we're going to take our carbons, and instead of drawing out each of our hydrogens individually, we're going to put them all together and use a subscript to indicate, again, the number of hydrogens. So we're taking all the hydrogens bonded to that carbon and just putting them next to that carbon with our subscript. Now I'm actually going to rearrange this, right? So far I just put them right there next to my carbon, but normally in our condensed formula we're going to put those to the right of our carbon. So this is a CH3. It's a carbon of 3 hydrogens bonded to it. Now we go on and we put our next carbon, and that carbon is connected to this carbon, so we put it right next to it in our condensed formula. And again, we have 2 hydrogens connected to it, and I condense those and put those right next to my carbon. And I can do this again, continuing down my chain, CH2, 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 and finally CH3, condensing this carbon at the end. So I've taken my structure here and just kind of squished it together or condensed it, put all my hydrogens right next to the carbons that they're bonded to, put my carbons in a sequence showing how they're bonded together. Now we can actually condense this a little bit further because so we have 3 identical carbons in the middle that each have 2 hydrogens. So we can actually condense this down. We use parentheses, put our CH2, and then we just put a 3 outside the parentheses to indicate that we have 3 of these CH2s repeating. So these are both different condensed formulas that we can use to represent that alkane there. Now, if I come over here to my branched alkane, so now I need to show this extra carbon coming out here in my condensed formula. So again, I'm going to start out the same way that I did before, just taking the carbon and then putting the hydrogens that are bonded to it right next to it. I have CH3, CH2, and now here I have CH, right? There's only 1 hydrogen bonded to this carbon, but now I have 2 CH3s bonded here. So there's 2 different ways I could do that. I could either show a bond coming out to that CH3, my branch. So there's one possibility. Or, since these are both identical CH3s, I could use my same parentheses approach here. So I draw it out, CH3, CH2, CH, and then in parentheses I put my 2 identical CH3s that are attached to my carbon here with a single hydrogen. 2 different condensed formulas. Both are equivalent ways of representing this branched alkane. Now, as we can see, if we compare our two condensed formulas, now we do have a way of representing that difference in structure that makes these two structural isomers unique. Our next method for representing our organic molecules is the skeletal or bond line structure. And this is my personal favorite. This is what we'll use most commonly in organic chemistry. We're going to take a step further beyond our condensed formula, and we're not even going to show our actual hydrogens or carbons anymore. We're just going to use lines to represent everything that we have in our structures here. So the key here with our skeletal structures is that we're going to draw a line, and at each endpoint or vertex of our line is going to be one carbon. So if I go over here to my alkane over here on the right, so I start out at the end of a line, and that's my first carbon, and then I draw my line until I hit the second carbon. So my line is going to end here, and it's going to go off at an angle over here. One carbon, second carbon, third carbon at each endpoint of my line, fourth carbon, and fifth carbon. So there's a carbon represented at each point, each vertex of my line, and I'm not going to show the hydrogens at all. So this is actually going to be my complete structure here of my alkane. Now notice, of course, you can draw this very quickly, but you might say, well, it's not complete, right? We don't actually show our hydrogens. But if you remember, we can actually predict how many hydrogens there are connected to each carbon, right? We know that each carbon needs 4 bonds. We know where all of our carbons are, right? Our carbons are at each of these vertexes or endpoints. We know each carbon needs 4 bonds, and so we can just add hydrogens on until each of our carbons has 4 bonds. And you can see we can quickly identify the full structural formula from just our skeletal bond line structure. So it's a little bit trickier because you have to kind of fill in the extra hydrogens just by knowing that each of your carbons will have 4 bonds, but it's very fast and convenient to draw. We can go over here to our branched alkane. We can do the same thing. 1, 2, 3, 4. There's my 4 carbons that are connected together in a line. And then I add my 1 additional branching carbon down here. Again, I'm not showing any of the hydrogens. They just, we know that they're there in order to fill in our 4 bonds for each carbon. So again, I would have my carbons at each endpoint here, each vertex. And I can fill in my hydrogens to get to the full 4 bonds per carbon. So the nice thing about our skeletal structures is that we avoid the extra step of having to draw each of my letters representing my atoms. Right? I know that I have carbons wherever my line ends. I know that I have hydrogens in order to fill up everything else. We can also add in other atoms as well. If we have other atoms present, we would just write directly what those atoms are. So here I have an oxygen connected to my, what was my same alkane structure from before. That oxygen also has a hydrogen. In this case, we do include the hydrogen. So we include hydrogens whenever they're attached to non-carbon atoms. We exclude them whenever they're attached to our carbons here. So it's a very fast and convenient way of representing molecules. We can even represent very large molecules quite quickly. Right? So I could draw out a much larger molecule. So this is a portion of the structure for cholesterol. Notice we have our carbons here. So again, our carbons will be at each endpoint. And we have them connected together in this ring-like system. So we actually refer to this as a cycloalkane. Right? So it's still an alkane where there's just carbon-carbon single bonds, and of course there would be hydrogens bonded on here to get up to our 4 bonds per carbon, but they're connected together in this cyclic system where we can kind of go around in a cycle to create our cycloalkane. So here I have my structure, which has, so I have 17 carbons total here, and I drew it out within a matter of a few seconds. If I was going to draw out all of my carbons and all of my hydrogens here, that would take me a couple minutes to draw. But I can quickly draw this large, complex biological molecule using my skeletal formula. So throughout the rest of organic chemistry, we'll mostly rely on these skeletal structures in order to quickly draw the organic molecules that we're interested in.